GCSE Science Boss back with another one. Sorry about taking so long to be uploading content, but GCSE Science Boss has been very, very busy. Anyways, I'm going to be looking at electromagnetism today. This is because I got a message asking me to go through Fleming's left-hand rule. But before I can go through all of that, I decided I'll just go from the very start of magnets and electromagnetism. All right, here goes. Let's go. So, the end of each magnet, as you can see here, the end of each magnet is called a pole. Okay, so you can see the north pole, you can see the south pole. Okay, good. So the magnets, if you place some iron filings around the magnet, you'll notice right here that the iron filings, they're quite close, but the further away from the poles that you go, the distribution is quite further away. And also you'll notice that a particular pattern begins to form. All right, this is caused by a magnetic field. Okay, and that field, it always runs from north to south. However, you can't tell that from the iron filings here. If you had a magnet, a plotting compass rather, that plotting compass would show you that the magnetic field is always running from north to south. Okay, always. So if I go back here, it's going to be running from north to south if you place your plotting compass at different points. Okay, good. You'll also notice that the poles, this is where the force of the magnetic field is strongest. And how do we know that it's the strongest? The lines are closer there. So therefore, when you're drawing your magnetic field lines, the lines need to be very, very close at points like these. And the further away you go, the further the distance between those lines. Okay, and it always runs from north to south. All right, the other thing that you need to appreciate is that if you have a wire, okay, and that wire is carrying current, then that wire also has a magnetic field around it. How do we know this again? Iron filings. Okay, so you can see the circular patterns there being formed. However, you can't tell the direction. Now, how would you tell the direction? You'll be able to tell the direction by using a plotting compass. Okay, so here's my compass here. The current is going from positive to negative, conventional current. So the current is going downwards. And as you can see here, the direction of the magnetic field is going in a clockwise direction. Now, you should be able to tell what direction is going in by using the right hand grip rule. Okay, so if the current is going upwards, you grip it like that. All right, as shown in the diagram there, using your right hand. And as you can see, the um the direction of the current is going anti-clockwise. Okay, so that right hand grip rule is used to tell the direction of the magnetic field. Okay, so your thumb will show the direction of the current and your fingers will show the direction of the magnetic field. What magnetic field, you're probably wondering? This part here, which is being shown here, those circles. All right, good. All right, so if we change the direction of the current, now your thumb is going to be pointing downwards, and what's going to happen to the direction of the magnetic field is going to be opposite, and it's now going to be going in the clockwise direction. All right, now if I decide that I'm going to wrap these wires close to each other, okay, just keep wrapping it close to each other, the magnetic field, right, what will happen is that the magnetic field now becomes stronger. All right, or you could also increase the strength. This is now what we describe as a solenoid. So a solenoid are long coils of insulated wire. All right, and this can use in devices where you have a strong magnetic field is needed. Okay, you can also increase the current, and that will increase the magnetic field. And if you reverse the direction of the current, that will reverse the magnetic field as well. Okay, so you should be able to make sure you know how to draw the magnetic field, all right, produced by a solenoid. All right, and also inside the solenoid, the magnetic field lines are parallel to the axis. Okay, so you can see that parallel bit there. All right, so from that, we can then use the idea of a solenoid to then make an electromagnet. So an electromagnet, you have an iron core, you then have your coiled wire, and that is attached to some sort of power source there. So once you switch the battery on, this now becomes magnetic. If you switch it off, it's no longer magnetic as there's no current flowing. Okay, so that's an electromagnet there. Now, if you think about it, if you then place a current carrying conductor or current carrying wire inside another magnetic field, you now have two interactions of magnetic field, and that will then create a force. Now, what do you think will happen to that wire? That wire will now move, okay? However, there are some key points that you need to know, all right? As you can see here, this current is is going into the board, okay, or going into the computer, into the screen. If it's drawn like this, it's coming out towards you, okay, or out of the paper, or out of the screen, okay. So now you have the interaction of these two magnetic field. Which magnetic field? This one with the wire here, which is going into the board, and the magnetic field of these two permanent magnets right here. All right, and that interaction will then create a force on that wire, and this then leads to what is called the motor effect. Okay, good. So the motor effect is, as you can see here, current is flowing from positive towards the negative end, conventional current. Okay, good. All right, even though the electrons flowing the other way, but don't want to confuse it. So it's going to be flowing from positive to negative. All right, this will then cause the wire to shift outwards. All right, and that is known as the motor effect, that force. If we then change the current direction, the current carrying wire will actually shift inwards. Okay, good. So it will reverse the direction of the force on the wire. Now, how do you work out the direction of the force on the wire? We use Fleming's left hand rule. Okay, so as you can see, just remember that the magnetic field always runs from north to south. Current is always from positive to negative. All right, and then your thumb will tell you the direction. So if you line up your left hand as shown here, using this finger here, point it from the north to the south. Okay, good. Your first finger. All right, notice they're all 90 degrees to each other. All right, your current is coming out of the board right here, or out of your screen. All right, notice that your thumb is pointing upwards. That means that if I place this wire inside of this magnetic field, it will jump upwards. Okay, good. So you need to know this for Fleming's left-hand rule. So your thumb will show the motion, all right? Your first finger will show the magnetic field, and your second finger will show the current, or you point that into the current, okay? So let's see if you understand this. All right, so you can see magnetic field always from north to south. So your first finger, using your left hand, you're pointing that from north to south. The current is going downwards. So your second finger, you will have to then turn that finger downwards. Make sure that that finger is pointing downwards. All right, and then as you can see now, your thumb should be pointing towards you. Therefore, this wire, the direction is going to be towards you. Okay. What would happen if we then change the direction of the current? You would have to then, still keeping your left hand, first finger still pointing from north to south, okay? You're going to turn your second finger upwards because the current is going upwards. Your thumb should be pointing away from you into the phone screen or the computer or whatever device that you're watching this on, okay? Good. Now, that is Fleming's left-hand rule. Now, we can figure out what force, okay, is on that current carrying conductor. And that force, we can figure out that force or on that wire. We actually, the size of the current will affect the force. The length of the wire will affect the force. And the magnetic flux density will affect the force, okay? Good. Therefore, we use the formula F is equal to Bill. Okay? F is equal to B times I times L. But the good thing about it is that you will have the formula sheet in your exam. Okay, make sure you know your units, very very important. And if you want to put that into a formula equation, you definitely can. All right, F at the top, B, I, and L. Okay, good. So make sure you know your units. Now, how can we increase the motor effect? We can increase it. If you think about the formula, you can increase the current. You can increase the length of the wire or the number of turns on the wire, and you can also use a stronger magnet. Okay, good. Now, hopefully that summarizes that topic for you. All right, the motor effect. X is a short length of bare copper wire resting on two other wires. So this is your copper wire here resting on two other wires. So describe what happens to wire X when the current is switched on. So if you notice here, this is positive, this is negative, which means the current is going to be flowing there, coming forward there, and going to the negative end. That's conventional current. Now to figure out what's going to happen, it's a current carrying conductor inside a permanent magnet. So it's going to experience a force. It's going to experience a force based on the motor effect, okay? In what direction? Now, to know the direction, we're going to have to use Fleming's left-hand rule. So your first finger, line that up with your magnetic field, always from north to south. So your first finger needs to be going downwards, okay? Your second finger needs to be pointing towards you. Why? Because it's moving from positive to negative, which means, therefore, that the wire is going to jump to the right. So it's going to experience a force to the right. Okay. What difference do you notice if the following changes are made? A, if the magnetic field is reversed. So now, what does that mean? Your north pole would be now your south pole, and your south pole would now become your north pole. What changes would you notice? All right. So your first finger is pointing upwards. Second finger still coming out at you, your thumb is going to be pointing left. So it will go in the opposite direction. So the wire would go left. Okay, good. All right, so the wire would go left in the opposite direction. All right, that question was not there. So to the right, we go in the opposite direction in the left. Okay, here is another question. So a teacher demonstrated the motor effect. So now you have a current carrying conductor inside two permanent magnets. Explain why there's a force on the wire when there is a current. So when there's a current, there is a magnetic field around the wire. So there is a magnetic field around the wire. Around the wire. Okay? And then that magnetic field is going to interact with the permanent magnet. This magnetic field interacts with the permanent magnet. Okay? It interacts with the permanent magnet. Good? All right? I think that should be enough to get you your 2 marks. All right? And you know that it will then experience some sort of force. Okay? Good? Next up, explain how the direction of the force can be predicted. 3 marks. So how can we predict the direction of the force? We have to use Fleming's left-hand rule. Use Fleming's, not GCSE boss. You're going to use Fleming's left-hand rule. Okay, but obviously that's not going to be enough to give us 3 marks. So when you use Fleming's left-hand rule, you're going to have to then explain Fleming's left-hand rule. All right, so your first finger, all right, your first finger here, where are you going to put your first finger? Your first finger is going to point from north to south in the magnetic field. First finger points north to south, okay? So your first finger is going to be aligned like that, north to south. Your second finger is going to be your current, so that's going to be going in. So second finger. All right. Second finger, that's the current. So it's going to go in, which means therefore that the thumb is going to, the motion is going to be downwards. Oh, what's going on? Come on. Your thumb points downwards. Okay, good. All right, so you can see the thumb will show the direction, the thumb points downwards. Okay, Fleming's left hand will make sure that you've explained that. Now, final question that we go through. This one is a calculation question. In one experiment, the teacher determined that the force on the wire is 2.14 millinewtons. Watch out for that, 4 marks. The current in the wire was 0.3 A. The length of the wire was within the magnetic field was 0.048 meters. Calculate the magnetic flux density. Now, let's see what was given. We're given the force F, which is equal to 2.14 millinewtons. We're going to have to change that to newtons, okay? Which therefore means we're going to have to divide that by 1,000, okay? So just let me emphasize here, we're dividing by 1,000, so that's going to be equal to 0.00214 newtons. What else has been given in this question? They've given you the length of the wire, which is 0.048 meters. Okay, what else have they given to you? They've given you the current, 0.32 amperes. All right, then they've told you to use the equation sheet. F is equal to Bill. All right, then they want you to find the magnetic flux density. So you're trying to find B. So we don't know what B is. We're trying to find B. So we're going to have 0.00214 is equal to B, which we don't know, times the current, 0.32, times that by L, which is 0.048, okay? Therefore, B is going to be equal to 0.00214 all divided by 0.32 times 0.048. And when you've plugged those values into your calculator, you should get a value of 0.1393. However, 2 significant figures. Don't lose that 4th mark there. That's your 4th marking point. So that's going to be 0.14. Okay? All right. Just comment below. Let me know what part you understood. If there's a part that you really think I need to go over. And make sure that you're hitting that subscribe button. Make sure that you're letting your friends know that GCSE Science Boss is here and going through lots of content for your GCSE. All the best in your GCSE 2024. I'm out.